This is 1.1, this is formula, equations and amounts of substance. So there are 7 different parts to this topic. The first one is writing formulae, and that is being able to write the formula of an ionic compound by predicting the ionic charge from the position of an element in the periodic table and by recalling molecular ions and their formulae. The second one is writing and balancing equations for unfamiliar reactions given appropriate information. Then you have to be able to write full and ionic balanced equations, including state symbols for all the reactions that have been studied in the course. So anything that has appeared, you have to be able to write that reaction. You'd be expected to have learnt it. And the next part was about Avogadro's constant, defining and demonstrating understanding of the terms Avogadro's constant, the mole and molar mass. Then using Avogadro's constant in calculations. The sixth part is calculating reacting masses of substances, and that is including examples in which some reactants are in excess. And finally, it was about hydrated and anhydrous substances. So knowing and understanding the terms anhydrous, hydrated, water of crystallisation, and also being able to calculate the moles of water of crystallisation present from percentage composition, mass composition, or from experimental data. So that's everything we're going to look at today. The first thing is ionic formulae. So an ionic formula or chemical formula is a shorthand method of describing the atoms in a chemical. So the chemical formula of an ionic compound tells you which elements it contains. So for example, FeSO4 has iron, sulfur and oxygen, and it tells you the ratio of metals to non-metal ions. So NaCl is 1 chloride ion for each sodium, where MgCl2 would be 2 chloride ions for every magnesium ion. You can work out the formula of compounds containing metals from the charges on the ions. So for group 1, the charge is +1. For group 2, it's +2. And for group 3, it's +3. For the transition metals, you'll see the charge the oxidation state in brackets. So you just translate that into a charge. For non-metals, if you have group 7, that's going to be minus. Group 6 is 2 minus, and group 5 is 3 minus. So you would be expected to be able to work out the ratio of ions present given the charges. We also looked at how to do that using valencies as well, and you can do that if that's easier for you. You do need to be able to write and recall the formula of different molecular ions. So they're species which have 2 or more atoms covalently bonded and have an overall charge. So the common examples that we looked at are here, and I've written them out already. So we have sulfate, which is SO4 2 minus, we have sulfite, which is SO4 3 minus, and you see the difference between these. Sulfate has 4 oxygens, sulfite has 3, and you'll notice that the other ones, nitrate, nitrite, hypochlorite and hypochlorite, the difference really is the number of oxygen atoms present. So then thiosulfate, S2O3 2 minus, hydrogen sulfate is HSO4 minus. And you'll notice that when there's a hydrogen present with the sulfate, you're just taking off a +1 charge because hydrogen is +1. The same with hydrogen carbonate and carbonate. Hydrogen carbonate is HCO3 minus and carbonate is CO3 2 minus. So nitrate is NO3 minus, nitrite NO2 minus. Phosphate is probably the trickiest one. It's PO4 3 minus. And then we'll have chlorate and hypochlorite. So chloride, of course, is Cl minus, but chlorate is ClO3 minus, and hypochlorite is ClO minus. So the one with the fewer oxygens is the ite. Hydroxide, you should all know, is OH minus. Dichromate, Cr2O7 2 minus, and chromate, CrO4 2 minus. Dichromate has 2 chromiums, that's how you remember which one's which. Then with manganate 7, which is your MnO4 minus, and ammonium, which is NH4 plus. So the next part is about chemical equations, and you're all familiar with chemical equations in that we write them all the time. We write word equations, and you also have to be able to write symbol equations. So when you're writing a symbol equation, you're looking for what is the symbol for the element. So we've got Mg, oxygen is diatomic, so it's O2, and then magnesium oxide is MgO. Now, when you write an equation, we consider that everything on the left of the equation is reactants, and everything on the right is products. And we always do an arrow, which means gives you or makes. So when we look at this equation, it's very obvious when you look at it that it's not balanced. And what you need to do to balance it is to make sure that there are the same number of atoms on each side. So at the minute we have one magnesium here, we have two oxygens, and we have one magnesium and one oxygen. So to balance that up, we need to add another magnesium oxide, because that will give us another lot of oxygen. So if I put a 2 here, that means now I have 2 magnesium and I have 2 oxygen. That means my magnesium oxide now has thrown out this side of the equation because I need another magnesium here. So what I'm going to do is add another magnesium by putting the big 2 in front. So when you're balancing equations, it's really important to follow these steps. The first thing is to count the number of atoms on each side of the equation. So if the numbers of each type of atom is not the same, it needs to be balanced. So you put big numbers in front of the formula which contains the atoms that don't balance, and then you continue until the number of atoms on each side is the same. Now it is really, really, really important. Do not change, and you know what I'm going to say, the small numbers. And it's the classic example, of changing H2O to H2O2 rather than putting a 2 in front of the H2O. Some people would put a 2 on the oxygen to try and balance it up that way. Can't do that, folks, because that changes what the actual substance is. So you're changing what the equation says if you do that. Okay. That leads us into ionic equations. Now, these only involve the species undergoing change in the equation or in the reaction. And any ions which are the same at the start and finish are called spectator ions. So the example I have here is magnesium and hydrochloric acid reacting to give magnesium chloride and hydrogen. And you'll notice that the state symbols have been put in here. So S is solid, AQ for in solution, G is for gas, and the one that isn't there at the minute is L for liquid. When we look at the ionic equation for this same reaction, what we see is we only take into account the things which change. So the magnesium is changing to Mg2+, and it's aqueous. And the hydrogen, so here it's H+, and it's changing to hydrogen gas. So the chlorine, you'll notice, isn't involved. It's the same on each side, because chlorine here would be Cl-, and here it's also Cl-. It is a spectator ion because it's the same on both sides, so it doesn't actually feature in the ionic equation at the end. Okay. So the next part of this topic was about numbers of particles, and what you really need to make sure you know is your definitions for these parts. So the relative atomic mass is the average or weighted mean mass of an atom of an element relative to 1/12 of the mass of an atom of carbon-12. 1 mole is 6.02 by 10 to the power of 23 atoms or molecules, depending what you're looking at, and that number is Avogadro's constant. So you need to be able to relate the number of moles to the mass and the formula mass, and also the number of particles in a mole and Avogadro's constant. So you need the formula to do that. And the formula that we use are the number of moles is equal to the particles divided by Avogadro's constant, L. So again, this is and that is 6.02 by 10 to the power of 23. Now, I know some of you like the triangles, and if we were to use a triangle for this, that would become moles, particles, and then L. And in the other one that you know and love, number of moles is mass divided by the formula mass. So our triangle for that would be the moles here, and mass, and then formula mass. So you need to be able to use both of those in calculations to work out if you're given the number of moles and the number of particles, or sorry, the number of moles and asked how many particles there are. You know Avogadro's constant, you go ahead and work that out. Or for most of your reacting mass questions, it's going to be number of moles is mass divided by the formula mass. So when you're doing a reacting mass question, the first thing you have to do is write the balanced equation. If you don't balance your equation, it's not going to work. Then you calculate the number of moles of the reactant. And it's just a matter of looking at the question, highlighting what there is, and working out what it actually is asking you to calculate. And it's worth taking a bit of time when you're reading the question to highlight or underline or circle, you know, the terms and the amounts that you're given. Then you're going to use the stoichiometry of the equation to calculate the number of moles of product. So by stoichiometry, I mean the number of moles in the balanced equation. So in that example that we looked at earlier on, which was Mg plus O2, gives you MgO, needed 2 magnesium oxide and 2 magnesium to balance the equation. So that's the stoichiometry. It's the ratio that the reactants and products are occur in the equation. So if you've got 2 moles of magnesium here, you'll produce 2 moles of magnesium oxide. Or if you've got 1 mole of oxygen, you'll produce 2 moles of magnesium oxide. So once you know the number of moles of the reactant, you can work out the number of moles of the product just by using that ratio. And then you convert the number of moles of product to mass, and that's your question done. So the last little bit of this topic is about hydrated ionic compounds. So when we think of hydrated compounds, we're talking about the water of crystallization in a structure. So water of crystallization and this is something that comes up all the time. It's water which is chemically bonded within a crystal structure. That's another definition that you definitely need to know. So we refer to substances hydrated. They contain water of crystallization. And anhydrous, which don't contain. The water of crystallization. Okay, so definitely make sure that you learn those definitions. All right. Now there was a little experiment that we did, which was calculating how much water of crystallization there was in a hydrated salt. And we can do that because most hydrated salts lose their water of crystallization when you heat them up. So the apparatus you would need for that would be a crucible. And then you put the hydrated salt in the crucible. The crucible then sits on a pipe clay triangle. And on a tripod. And on a heat-proof mat. So what you do is you heat the whole thing, and you basically are heating it until you achieve a constant mass. And if you remember, we did that. We had a lid on the crucible, we lifted it off, and then we kept heating it until the mass was the same when we weighed it, or when we used the balance on a couple of different occasions. You need to make sure that it cools down before you set it on the balance, because if you don't, then it can wreck your balance. So that's when you have to take care. Okay, so at this point, I'm going to give you a chance to go and do the questions which I've attached, which are from the CF fact file. I put the whole fact file on there, which is just basically what I've gone through in this video, but I'm going to say you can pause the video at this point and then come back to it if you need to look at the answers. Okay? Okay. So I've printed out the questions here from the fact files, and I thought it'd be useful if I actually go through the answers, because sometimes when you read the answers from the fact files, you don't really understand what's going on. So the first one here, the answer to the question, first of all, is B. So the question says, phosphoric acid is manufactured by the reaction of sulfuric acid with calcium phosphate according to this equation. 3H2SO4 and Ca3PO4 twice gives you 2H3PO4 and 3CaSO4. So what mass of phosphoric acid, I'm going to underline that, would be obtained from reacting 60 kilograms of sulfuric acid with 60 kilograms of calcium phosphate? So what we want to do is work out the ratio of what's reacting here, and we can work out then how much we're going to get. So a multiple choice question like this shouldn't take you too long to do. But if we look first of all at the moles of sulfuric acid, so we've got 60 kilograms, which is 60,000 grams. Okay, so remember you have to convert things to grams when you're working with kilograms like this. So your number of moles is the mass divided by the formula mass. The formula mass of sulfuric acid is 98. So 60,000 divided by 98, and that gives me 612.24 moles. Okay. The next part of the question is to work out the number of moles of calcium phosphate. So in this case again it's 60,000 grams, and the formula mass for calcium phosphate is 310. So the number of moles of calcium phosphate is 193.55. So when I look at the balanced equation, I can see here that 3 moles of the sulfuric acid will react with 1 mole of calcium phosphate. So what I want to see here is which is the limiting reagent, in other words, which one is in excess. So I can see I've got 193.55 moles of calcium phosphate, I've got 612.24 moles of the sulfuric acid. So that amount of sulfuric acid would react with basically 1/3 of the number of moles. So 612.24 divided by 3, which is 204.08 moles of the calcium phosphate. Now, we don't have 204 moles here. We only have 193.55. So that is the limiting reagent. So we go back to beginning, we have number of moles of then the H3PO4 formed is from the stoichiometry with 1 mole of calcium phosphate to 2 of the H3PO4. So we're looking at this number of moles times 2 because we've got a 1 to 2 ratio. So that is 387.1 moles of the this phosphate that's formed. Now we want to know what mass that is. So 387.1 times 98, which is the formula mass, gives us a huge number, 37935.8, which when we convert into kilograms is 38 kilograms, which is B. So that's a whole lot of working out, but we got there in the end. Okay, sorry, I'll just move that down so you can see what I was writing there. I'd moved off the screen, apologies. Okay, the next one's just a good bit simpler. So it says you're required to plan an experiment to determine the degree of hydration in a sample of sodium carbonate. If the sample of hydrated sodium carbonate is heated in a crucible to constant mass, an appropriate mass is measured, the value of X in the formula can be found. So explain what is meant by the term hydrated. It's very straightforward. It just means it contains water of crystallization. Okay, so that's the sort of question you really hope to get in this topic. The next bit asks you to draw a labeled diagram to show the apparatus which could be used to heat the hydrated sodium carbonate. So the things that they're looking for in here to get you your marks. First one is a crucible containing the sodium carbonate, so that is the hydrated Na2CO3, and then that is a crucible, then piped a triangle and a tripod, and your tripod, and finally the heat-proof mat. Now, when you're drawing diagrams in your AS exam, you're absolutely going to use a pencil and a ruler. I'm just doing them very roughly here because it's just a quick video. Okay, so make sure you are equipped in your exam with a pencil and ruler if you have to draw the diagrams. Okay. Next part of the question. What masses should be recorded before heating the hydrated sodium carbonate? So before you actually heat it, you need to record a couple of things. The first thing is the mass of the empty crucible. And the second one is the mass of the crucible plus the hydrated sodium carbonate. Okay. Then it says the hydrated sodium carbonate is heated to remove all the water. What steps would you take to ensure that it all been removed? So that's what I was saying about in the video earlier. So you heat it. That's your first step. Your second step is just to repeat until you get 2 consecutive masses which are the same. Now, one safety precaution which should be taken, which should be followed before weighing, well, that's allow it to cool. So it does take quite a while if you have to heat it, cool it, heat it, cool it, heat it, cool it, but you have to make sure that you do it right and you get it to that constant mass. So the last bit involves the calculation. Get that in shot. Okay. So when 11.44 grams of hydrated sodium carbonate was heated, 4.24 grams of anhydrous sodium carbonate was formed. So I'm going to circle and underline so that I know what is being made. So it says, what is the mass of water lost? So we're looking at the total mass, which is 11.44. Take away the mass which is left, which is 4.24, and that gives you 7.2 grams. Make sure you always write your units, you know, and show you're working out as well, because if you make a silly calculation error, you do get credited with an error carried forward in a lot of these questions. So then the number of moles of water lost, number of moles is mass over the RFM. So that's 7.2 divided by 18, which is 0.4 moles. And then the number of moles of the anhydrous sodium carbonate formed. So we know that the mass is 4.24 and formula mass is 106. So that gives us 0.04 moles. So then X, we're just looking at a ratio. So we have 0.04 to 0.04.